Okay, I thank the organizer for the invitation. It's an honor to be at this conference, and I think I learned a lot of techniques from reading papers by Ramurthy. And they are all very extremely clearly written and very easy to read. I think even undergraduate students can try to read them. And thankfully they are all freely available on his web page. You don't need credit cards to download them. Okay, so many papers of Ram and Kumar Murthy deal with question of lacunarity of modular forms, and what I'm going to talk about is related to that. So like many problems, it begins with a question of Sayre. So in his famous paper on applications of Chebotarev density theorem, he asked the following question. So first of all, F is a primitive this board is completely wet. Holomorphic cusp form of, say, weight K and level Q. So here primitive means it's a new form. So and I assume that it's not a CM form. Because for CM forms we know that there are many Fourier coefficients which are 0. And the question is the following. The question is whether it can happen that there is a long string of consecutive Fourier coefficients which are all 0. So F has a Fourier expansion, some lambda Fn e to the power 2 pi I n z. Let's say if it's a cusp, yeah, holomorphic cusp form, okay. Okay, and we look at the sequence lambda Fn. And the question is, so I define something called IFN, that's Sayre's notation. This is max over K such that lambda F n plus 1, lambda F n plus 2 up to lambda F n plus K, and they are all 0. So starting from n, how we want all the Fourier coefficients from n plus 1 to n plus k to be 0. And we want to give an upper bound of IFN. We suspect it cannot be very large. So Sayre asks, is it true that IFN is O of n to the 1 minus epsilon for some epsilon positive? Now it's somewhat strange that Sayre should ask this question, because Sayre certainly knew about Rankin-Selberg work estimate, from which it follows trivially. So I'll recall what it says. It says that normalize by dividing by n to the k minus 1 by 2 and then square it n up to x. This is a constant that depends on x. It's essentially L1 sin square plus O of x to 3 over 5. So you put x equals x plus h and subtract this, then you will get main term h and the error term O of x to the 3/5. So as soon as h is larger than x to the 3/5, you have a main term. So this implies I can always get if n is less than n to the 3/5 plus epsilon, and 3/5 is less than 1. So this question is not very hard. And now the question is how small, we want to be better upper bound of this. So how small, so what's the smallest theta so that if of n is O of n to the theta. Okay. And there have been a lot of works on this problem in recent years. So I will give a brief history of that. God. This is not good. No, both are. Okay. Making a difference. Yeah, I think the wet mop is better. This wet thing will be better, I think. Okay, anyway, so all the work that has been done so far, it was started by Balog and Ono. It's a paper in Journal of Number Theory in 2001. So they noticed that this problem can be connected to an old problem in number theory, that of B-free numbers. So Erdős introduced something called B-free numbers. These are generalization of square-free numbers. So what's a B-free number? So let B be a set of integers. And we assume that, so suppose B is B1, B2, etc., such that sum over 1 by Bi is convergent. And we assume that Bi and Bj are co-prime when I and J are distinct. Then, so the theorem by Erdős from 1966 that says that the interval x to x plus x to the 1 minus epsilon contains, you haven't defined the B-free numbers. So B is a set satisfying this property, and then an integer n is called B-free if no Bi divides n. Okay, no elements of B should divide n. And Erdős showed that x to x plus x to the 1 minus epsilon contains a B-free numbers for some epsilon and for all x sufficiently large. So henceforth I am going to omit this expression that for all x sufficiently large. Whenever I write x, that would mean for all x sufficiently large. Okay, so this already says something about IFN, and that's what Balog and Uno noticed, and it's in the following way. So we want to apply this result, and we have to define our set B in an appropriate way. So we recall the theorem of Serre, that says that number of primes up to x such that lambda f of p is 0, this set is small. So this is O of x divided by log x to the 1 plus 1/2 minus epsilon for some epsilon. The point is this exponent is larger than 1, and therefore by partial summation you can get, so this theorem implies sum of 1 by p such that lambda f of p is 0. That converges, that's just calculus. And so we can apply this result, Erdős, by defining the set B to be the set of primes P up to x such that lambda f p is 0. But we need to put some more things to make, oh God, okay. Yeah, so can you give me that? No, that cloth. Yeah, this. Anyway, so what we are going to take is B should be first of all prime with lambda f of p, not just x, just primes with lambda f p 0. Union squares, union those primes that divide the level. What this result tells you is that for x sufficiently large, there exists an integer in this interval which is B free, which is free of factors from this, and then the multiplicativity of lambda f n will be product over lambda f p to the alpha divides n. So that will tell you that all these factors are non-zero, and therefore this is non-zero. So that's another solution to Serre's question. And now, since it has been connected to B-free numbers, and there were works by various mathematicians on improving this, all those things will apply to the question about IFN. So what Balog and, okay, so I will, so this was Erdős in 1966, and so this has a B-free number. For theta equals half plus epsilon. This is Zemeredy. This was shown by Zemeredy in 1970s sometime. And then there were a lot of improvements by various mathematicians. And recently Wu made a lot of, so Wu showed that one can take theta to be 17/41 plus epsilon, I think 93. And all these results use very difficult results of Fourier and Ivanich and exponential sums. And the best results known today is due to Kowalski, Robert, and Wu. I think this is from around 2007. And theta is now 7/17. So Barlow and Ono used this result 17/41, and this is the best known bound for general modular forms. So what we are going to talk about is an improvement of this in some special case, namely when level is 1. So theorem, so everything is joined with Soumya, if we were to write. If f has level 1, then I f of n is O of n to the 1/4 plus epsilon, and the constant depends on the weight of the modular form. And Kowalski-Robert Wu's result would imply that IFN is O of n to the 7/17 and 1/4 is smaller than 7/17. Okay, so we don't use any B-free numbers in our proof, it's a completely different proof. We use congruences. So if something is non-zero mod some integer, then it is non-zero. That's what we use. And so Ramanujan already proved a lot of congruences for tau n, and there is a famous result by Hatada, famous paper of Hatada from 1980s, in Math 111 probably, where he gave a lot of congruences for any Hecke eigenform on SL to Z. So one of the congruences says the following, which is what I will need most, is congruent to p plus 1 mod 4. Maybe it is true mod 8 also for primes p different from 2. So if we could show that between x and x plus x to the 1/4 there exists an integer which is product of distinct primes which are congruent to 1 mod 4. So if if p is congruent to 1 mod 4, then lambda f of p is non-zero. That's what this congruence will tell us. So suppose we can prove that x to x plus c x to the theta contains an integer which is product of distinct primes which are all 1 mod 4. Then I can say that between x and x plus O of x to the theta there is an integer which is n for which lambda f n is non-zero. The problem is making such a statement is very difficult. Okay. So what we are going to do is, so first of all we can do the following. So we look at sum of squares. So we know that if n is the sum of two squares, then n is of the form 2 to the alpha p congruent to 1 mod 4, pi congruent to 1 mod 4, qj congruent to 2 beta j, qj congruent to 3 mod 4, right? The primes which are 3 mod 4 must occur with even coefficient. Now, if we look at sum of two squares which are themselves square free, then these factors will be gone. So, if n is square free as well, then n is of the form possibly with 2 and p congruent to 1 mod 4 times pi. And then by multiplicativity it will be lambda f of n would be lambda f of 2 times product lambda f of pi. And since pi is 1 mod 4, lambda f of pi is non-zero, and therefore this product is non-zero, except at the prime 2 there may be a problem. Now there is a result by Conan which implies that lambda f of 2 is always non-zero. So if an integer is square free and it is expressible as sum of two squares, then lambda f of n is non-zero. And counting these, proving the existence of these integers in short interval is an easier problem. And this is not very different from the Gauss circle problem. So this exponential sum A process B process will apply, and the best result results from the theory of exponential sum. Implies the following, that IFN O of this is I think 131 over 416, and this follows from Graham and Kolesnik. And IFN is O of n to the 1/4 plus epsilon. If we assume a strong conjecture, namely exponent pair, and here these implied constants in the O term, they have nothing to do with the modular forms, they are absolute constants. And in this theorem that I am going to talk about now, the implied constant depends on k. Alright, so okay, now I talk about this theorem. Okay, so see, earlier we were talking about square free integers which are sum of two squares, which are a little difficult, but if we didn't have the square free condition and the question was proving the existence of integers which are sum of two squares in short interval, that's also an old problem, and we can do slightly better for them. And there is an old theorem of Bamba and Chawla from 1950s that says that x2 x plus constant times x to 1/4 contains an integer which is sum of 2 square. And the proof is very elementary. The proof is like this. The idea is to be as greedy as possible. You define A to be the floor of square root of x, h to be x minus a square, and b to be square root of h floor plus 1. Then x a square plus b square some 10 x plus 10 x to the 1/4 as long as x is sufficiently large. But the problem is we cannot apply this result to our situation, because when I look at prime factorization of an integer like this, a square plus b square, there will be previous prime powers. So how to deal with that? Then we use a technical lemma. So this follows from some lemma of a paper by Raman Kumar Murthy and some result in Kowalski, Robert and Wu. So it says that lambda f p non-zero implies lambda f of p to the n is also non-zero for all n, provided p is sufficiently large. And if this Hecke eigenvalues lambda fn are rational integers, then this is true for all primes p. Okay. So we can. So in our theorem there is a dependence of the constant on the weight, but if we knew that Hecke eigenvalues are integers, then we can make that implied constant absolute constant. Okay. So I am not going to say anything about the proof of this lemma, and I'll just talk about how to apply that. So. So basically the theorem follows from the following proposition. So there exists an integer m that depends on f. So given f, there exists mf which I can take to be even, such that if n is a sum of two squares, which I denote by this, and if n is prime to mf, then lambda f of n is non-zero. So if we assume this proposition, then an argument very similar to this argument you have to modify it a little bit, will give you the theorem. And so the only thing left is to prove the proposition, and the proposition follows from that technical lemma, because any n which is sum of two squares will look like this. So by multiplicativity, I will have to look at lambda f of 2 to the alpha, etc. But since n is co-prime to mf, this factor won't come, because I will take mf to be even. And this technical lemma says that for all primes, lambda f of p non-zero implies lambda f of prime powers is also non-zero, as long as p is not very small. Okay, so mf will be basically product of those exceptional primes, the small primes. Okay, that's how the dependence on f comes. And so for example here, lambda f of p is non-zero, we have already seen that, when p is 1 mod 4. So lambda f of pi to the alpha is also non-zero. And when q is 3 mod 4, so fortunately we have even exponents. If we had odd exponent there, we would be in trouble. But so for example, if q is 3 mod 4, I will show that lambda f of q square is non-zero, and that follows from Hecke relation. This is lambda f of q whole square minus q to the k minus 1. And so modulo 4, lambda f of q will be q plus 1. So this is q plus 1. And q is 3 mod 4, so this is 0, and therefore this is non-zero. And by induction or otherwise you can show that all even powers, lambda f of q to the power 2 beta, will be non-zero. So therefore lambda f of n is also non-zero. So that's how we finish the proof. Okay, I think that's all we want to say.